Hello, today we're going to review the difference between additive and proportional relationships in linear equations. For the last couple of weeks, we've been discussing the difference between additive and proportional relationships, and we're going to identify differences between the two in the three forms of equations, graphs, and tables. In an equation, we know that x and y are being related by either multiplying or adding or subtracting. If we see an equation where they are related by addition or subtraction, then it is an additive relationship. The amount that's being added or subtracted is at the end, it's usually plus or minus, and we use the letter b to denote that value. Remember that b is the y-intercept, which is where your graph crosses the y-axis on the coordinate plane. When you're looking to see if an equation is additive, you'll see that after x, y is equal to x, and then you should see a plus, such as this plus 4, or a minus, such as this minus 8. This is our value of b, or our y-intercept. Remember that plus 4 means that it's 4 above the origin, and minus 8 would mean that it is 8 below the origin. In a proportional equation, x and y are being related by multiplication or division, and that value of m is called the constant of proportionality, whatever we're multiplying by each time. M is the coefficient, or the number in front of x that you're multiplying by. It's also representative of our slope, or the steepness of the line. In our equation, y is equal to 4x, you can see that we have a coefficient of 4. We're multiplying 4 times x. So we know that it's multiplication, which means it's a proportional relationship, and m is equal to 4. The slope would be 4 over 1, rise 4, run 1. In our next equation, y is equal to 1/2 x. That means our coefficient, or the number we're multiplying x by, is 1/2. Okay? That could also be written as y is equal to x divided by 2. Remember that multiplying by half and dividing by 2 are functionally the same. And in this case, m is equal to 1/2. Try the following examples on your own and pause the video. And in a moment, unpause and we'll review. So, in our first example, y is equal to 2x. We notice that there's a 2 in front of the x as a coefficient. That means it's being multiplied by 2. So we know that this is a measure of slope of 2, and it is a proportional relationship. Going down, y is equal to x plus 4. We know that we're not multiplying or dividing, we're doing addition, and addition means it's an additive relationship. Our b, or y-intercept, would be plus 4. And the next one down, y is equal to x minus 1/2. Even though we're more commonly see fractions as a portion of slope, or a coefficient of x, we do see that it's after a minus sign. So that's okay, we're just subtracting half. That means our b, or y-intercept, is equal to 1/2, negative 1/2, and it is an additive relationship. In the equation y is equal to x, there's an invisible coefficient of 1. We can always assume there's 1 times x. We can also say they're probably adding 0. But since there's no change to either the slope or the y-intercept, we assume that this is neither relationship. It's just y is equal to x is neither. Finally, y is equal to x divided by 4. We know that we are dividing, which is a proportional relationship. Another way you could write that is y is equal to x times 1/4, or 1/4 x. Okay? So our slope in this case, or m, is 1/4. Hopefully, you're able to now determine the difference between additive and proportional equations. Now let's take a look at the difference between additive and proportional graphs. An additive graph can be identified because it does not go through the origin. Remember that adding or subtracting changes how far above or below 0 on the graph the line will be. So if we have added or subtracted, it's not going through the origin anymore. The y-intercept, or point at which it goes through the y-axis, will no longer be 0. In this example, our y-intercept is -3, where b is equal to -3. You can see that our line has moved 1, 2, 3 places below 0. So an additive graph has a change in the y-intercept, which means it's no longer through the origin, not through the origin. Another important thing to note is that it will not have a change in its slope. The slope of the line between any 2 points should be 1, up 1 over 1. You can identify a proportional graph because it will always go through the origin, or point 0, 0. Right? It will always go through the origin, and there should be a change in the slope. The slope should be anything greater than 1 or less than 1. Okay? It should be steeper or less steep than 1. Try these 5 examples and pause the video, and return to the video when you're ready to discuss. Okay, let's take each of these one at a time, beginning at the top left. I see that my graph goes through the origin. First thing I always check is, does it go through the origin or not? This one goes through the origin, which makes me think it's proportional. But before I can say for sure, I also need to check that its slope is not 1. I can't exactly tell what the slope is here. It looks like it's off the graph greater than 1, but I can tell that it doesn't go up 1 over 1. So it's steeper than a slope of 1. A slope of 1 is perfect diagonal, so it's not diagonal. So it has a slope of greater than 1, and it goes through the origin. It must be proportional. And the next graph, directly to the right, it does not go through the origin. Remember, I always look at the origin first. That tells me whether it's proportional or additive, and then I double check. So it doesn't go through the origin, which makes me think it's additive, but in order for it to be additive, it also must have a slope of 1. It has, right now, it goes through the y-axis at 2, so it has a y-intercept of 2, and it's going up 1 over 1. So it does have a slope of 1. That means it is an additive relationship. Next one, not through the origin. Looks like the y-intercept is between -3 and 4. That's okay. It can have a -3.5 y-intercept. That'd be fine. But it does look like it has a slope of 1. It's a little hard to tell, but if you try to go up 1 and over 1 with an estimation, you can see it's almost certainly a slope of 1. So this would be an additive relationship as well. Our graph on the bottom left goes through the origin and appears to have a slope of 1 up 1 over 2. So slope of 1/2, and it goes through the origin, means it's proportional. Our final graph goes through the origin, which makes me think it's proportional. But when I check, it also appears to have a slope of up 1 over 1. So even though this one does go through the origin, its slope hasn't changed. That means its y is equal to 1x plus 0, or just y is equal to x, which means it's neither additive or proportional. There's been no change to the y-intercept or the slope. The last representation we'll discuss are for tables. Additive and proportional tables, you should be able to find a pattern on how you get from x to y. In an additive table, to get from x to y, you're going to either be adding or subtracting some amount. It should be the same amount to get from the left to the right side each time. I usually ignore the negative pairs, and if I can find a 0, you should go with that, because that'll be the key to telling you what your y-intercept is. It's very easy to tell the change. What number plus 0 is equal to 3? It's an addition of 3. So 0 plus 3 is equal to 3. And then just double check that that pattern holds true for the other pairs. 1 plus 3 is 4, 2 plus 3 is 5. Okay, must be additive. In a proportional relationship, we're still looking to see how to get from x to y, but when we look in our table, we'll find that we're multiplying instead of adding. Okay? A key indicator is that if you see 0, 0, chances are you're multiplying. Now I'm going to look at one of the positive pairs to find the pattern. 1 times 2 would be 2. And then I double check, is 2 times 2 4? Yes. So I know that it is proportional, and our slope is 2, or m is 2. In our additive examples, remember, if you see a 0 for x, take a look at that pair first. I know that to get from 0 to 10, I'd have to add 10. So this one has to be additive with a y-intercept of 10. Some of them don't give you a 0 to work with. In that case, you can choose any pair. It might be easier to choose a pair where both values are positive. To get from 7 to 3, I would have to subtract. I'm going down. And I would subtract by 4. Then I can double check and make sure that subtracting by 4 works for the other values. In proportional, if you see 0, 0, double check some of your other numbers, but chances are you're multiplying, and it's a proportional relationship. Here we're multiplying by -3. If you don't see a 0, pick a positive pair, a pair where both values are positive. What would I have to do to get from 5 to 1? Probably divide by 5, or multiply by 1/5. Remember, division is also a part of a proportional relationship. Last chance to try these 5 examples, and then we'll review together. In our first table, I find that I have a 0 for x. That makes it easy. 0 to 1 would be plus 1. And I'm going to double check, does that work? 1 plus 1 is 2? Yes, this is additive. In my second table, there's no 0 for x. So I'm going to go check the first positive pair, 2 to 0. To get from 2 to 0, I'd have to subtract 2. Does that work for the next one? Yes, it does. This one's also additive. In the next table, I have 0, 0, which makes me think it's proportional. So I'm going to check and see, what would I multiply 1 by to get 7? 1 times 7 is 7. 2 times 7 is 14. So this is a proportional table. Here, to get from 0 to 4, I'd be adding 4. But if I try that here, it doesn't give me the same amount. Since there's no other number that would get me from 0 to 4, multiplying or adding, this is neither additive or proportional. And finally, in this one, it's a little tough because you have these fractions, but if I look at the two positives, how would I get from 3 to 1? I would divide by 3. So for each of these, to get from x to y, I'm dividing by 3, and division is part of our proportional relationship. I hope that you're able to now tell the difference between proportional and additive relationships in the 3 representations of equations, tables, and graphs.